Welcome back to our discussion about solving trig equations. And in this video, we're going to focus our attention on solving trig equations that are quadratic in form. We've already tackled a couple of different types of trig equations, but these are going to be something that looks familiar, something that looks like what we've done in algebra before, and we're going to treat it the same way. So let's jump in. But before we jump into that, we're going to introduce a new concept. In the past two videos, we've been talking about solving for general solutions or all possible solutions. We're going to introduce this concept here where we talk about solving for the principal solutions only. And all that means is we are wanting to identify the solutions that are found on one rotation of the unit circle. So everything from 0 to 2 pi, but nothing beyond that. Okay, so nothing negative and nothing greater than 2 pi. With these types of examples, we will be seeing equations that are quadratic in form. Okay, so if you have an equation that is quadratic in form, you are just going to treat it like a quadratic equation. And the way I'm going to show you how to do that is first set the equation equal to 0, and then we're going to sub out the trig function so that we can look at it more objectively like a true quadratic. And then we'll factor it and set each factor, and then set each factor equal to 0 and solve for x. So let's walk through that process. With this particular example, we have 2 cosine squared of x plus 3 cosine of x equals -1. Now we know this is quadratic in form because of two things. One, you have only one trig function within the equation. So all I see are cosines. I don't see sine, tangent, anything besides that, okay? The other thing is the highest degree is a squared, and I may or may not have a trig function that is not being squared. And I may or may not have a constant for that matter. The key thing is we're going to have no more than one trig function, and that trig function has at least one term that is raised to the second power. So first, let's set this equal to 0. So let's move that -1 to the left-hand side of the equation, and then we could say 2 cosine squared of x plus 3 cosine of x plus 1 is equal to 0. Now, we see that it's quadratic, but maybe it's harder to see it as a quadratic equation. So let's say that u is equal to cosine of x. Well, if u is equal to cosine of x, then 2 cosine squared of x would be the same as 2u squared. And 3 times cosine of x would be 3u. So I'm going to treat this like the equation 2u squared plus 3u plus 1 is equal to 0. Now, I'm going to go ahead and solve that quadratic, and you can use any method that works to solve this quadratic. I will rely on factoring because to me that is the fastest way. I know that this quadratic factors to 2u plus 1 times u plus 1 is equal to 0. Then I'll back substitute my original argument back in. So 2 cosine of x plus 1 times the cosine of x plus 1 is equal to 0. Now you can go ahead and solve for u and then back substitute. Either way is fine. So now I'm going to set each of those factors equal to 0 and solve. So 2 cosine of x plus 1 is equal to 0, and cosine of x plus 1 is equal to 0. Let's isolate the trig function. So we'll say the cosine of x is equal to -1/2 here and -1 here. And then pull the angles from the unit circle that have these cosines. Which angles have an x-coordinate of -1/2 and -1? Okay, there are 2 for the first one, so that will be at 2 pi over 3 and 4 pi over 3 on the left-hand side of the unit circle. And then where's a cosine -1? Which angle measures have an x value of -1? That will be at pi radians. Our solution set for this equation is pi, 2 pi over 3, and 4 pi over 3. Okay, so for these examples, remember that we are looking for exact principal solutions, and remember that principal solutions just means we're looking for only the solutions that are going to be on one rotation of the unit circle. And that means from 0 to 2 pi, but not including 2 pi. So let's start with this first one. 2 sine squared of x is equal to negative sine of x plus 1. All right, and in this case, we're going to bring everything to the left-hand side. So that will be 2 sine squared of x plus sine of x minus 1 is equal to 0. And then I will write this as a quadratic without the trig function. I will let my substitution be u is equal to sine of x, and then substitute that in. So I'd have 2u squared plus u minus 1 is equal to 0. All right, and so when I factor that, I'll end up with 2u minus 1 and u plus 1 is equal to 0. And now I'll back substitute my trig function. So I'd have 2 sine of x minus 1 times sine of x plus 1 is equal to 0. Set each of those factors equal to 0 and isolate the trig function. So the sine of x is equal to 1/2 and the sine of x is equal to -1. And so I'll get 2 answers out of that first equation and 1 out of the second. Which angles on the unit circle have a y-coordinate of 1/2 and -1? That will be at pi over 6 and 5 pi over 6 for this first one, and 3 pi over 2 for the second one. All right, and so that will be my solution set. Pi over 6, 5 pi over 6, and 3 pi over 2. For the second example, we're going to work it through the same way. We see it's a quadratic, one trig function. The maximum degree is a squared. So we can set the whole equation equal to 0. So we would say 2 sine squared of x minus 4 sine of x minus 6 is equal to 0. We will let our substitution be u is equal to sine of x. And we'll treat this like 2u squared minus 4u minus 6 is equal to 0. Well, right away you can factor out a 2, and then you would have u squared minus 2u minus 3 is equal to 0, which will factor to 2u plus 1, u minus 3 is equal to 0. Okay, so now back substitute, and we can say that we end up with 2 times sine of x plus 1 and sine of x minus 3. And that is all equal to 0. We're going to set those factors equal to 0. We don't need to worry about the 2 because we can just divide that out. And we would end up with the sine of x is equal to -1 and the sine of x is equal to 3. Now this is a little bit interesting, okay? Because we definitely know that the sine of x is equal to -1 at 3 pi over 2. But where is the sine of x equal to 3? And that's tricky because of y equals sine of x. You'll remember that the range of that graph only goes between -1 and 1. And so there is no solution from this factor. Okay, and that is because there's nothing that will satisfy this equation. So the only solution to this trig equation will be 3 pi over 2. A couple more examples for us to walk through, and look, these look a little simpler, okay, and in some ways they are. Notice that they're still quadratic in form, but there's no middle term. Okay, so let's take a look. This first example, 4 cosine squared of x is equal to 1. We will set that equal to 0 and subtract 1 on both sides. We'll say that that is 4 cosine squared of x minus 1 is equal to 0. And we will sub out the trig function, and we'll say that that is u is equal to cosine of x, and we would have 4u squared minus 1 is equal to 0. We know that this factors by 2u plus 1 and 2u minus 1 is equal to 0. And we will back substitute our trig function. So we would end up with 2 factors of 2 cosine of x minus 1 and 2 cosine of x plus 1 is equal to 0. Now, if I set both of those factors equal to 0 and isolate the trig function, we will end up with cosine of x is equal to 1/2 and cosine of x is equal to negative 1/2. And so we will end up with 4 solutions here, 2 from the left and 2 from the right. The angles on the unit circle that have an x coordinate of 1/2 are pi over 3 and 5 pi over 3. And the angles on the unit circle that have an x value of negative 1/2 are 2 pi over 3 and 4 pi over 3. So my solution set, pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3. So for these last 2 examples, we're going to try a different technique just because it can be done in a different way, and I wanted to show you a different method. Okay, so if you're looking at 9 times the tangent squared of x is equal to 3, do you notice right away that there's a common factor of 3 on both sides of the equation? Let's go ahead and divide that out. And we would end up with 3 times the tangent squared of x is equal to 1. Now let's go ahead and isolate our trig function, so divide both sides of the equation by 3. So now we have tangent squared of x is equal to 1/3. Now to isolate the trig function from that squaring, we're going to have to take a square root of both sides. And when we do that, we need to remember that we want a plus or minus on the other side of where that variable is, okay? So we would end up with the square root of tangent squared of x is equal to plus or minus the square root of 1/3. Now the square root and this square are going to undo each other. They're inverse operators, so we would just say that the left-hand side is now just going to be the tangent of x. And then the right-hand side is going to be this radical, but we really want to think about it as the square root of 1 over the square root of 3, okay? Because that's going to allow us to simplify it a little bit. All right, now remember that the square root of 1 is just 1, and then we would have 1 over the square root of 3. And so when we rationalize that, we would end up with the tangent of x is equal to plus or minus the square root of 3 over 3. And now we're going to rely on our knowledge of the unit circle. Where are there angles that have a tangent of x equal to square root of 3, either the plus or the minus? And we would find those at our 30-degree angles or our multiples of pi over 6 that don't simplify to pi over 3. And so we would end up with a positive tangent in the first and the third quadrant, so pi over 6 and 7 pi over 6, and a negative tangent in the second and fourth quadrant of 5 pi over 6 and 11 pi over 6. All right, and so that would give us our solution set. All right, this last example is going to be very similar. All right, so can you keep a step ahead of me? I'm going to give you a head start. Go ahead and see what you can do. What happens next? Hopefully you divided both sides of the equation by 2 and get 2 secant squared of x is equal to 1. Then divide out the 2 and get secant squared of x is equal to 1/2. Then we would end up with taking the square root of both sides here. So the square root of secant squared of x will equal plus or minus the square root of 1/2. So that would leave us with the secant of x is equal to plus or minus 1 over the square root of 2. And we can separate those, right? So 1 over the square root of 2. So here, when we take the square root of 1, we're just going to get 1. And so we will have the secant of x is equal to positive and negative 1 over the square root of 2. Now, we know that we would want to rationalize this, but I'm going to wait on that because we're dealing with secant. And when we're dealing with secant, it's often easier to deal with its reciprocal. So let's reciprocate both sides of the equation. So 1 over the secant of x will give us cosine of x. 1 over negative 1 over the square root of 2 will just give us negative square root of 2. And likewise, to the right, we would have cosine of x is equal to the square root of 2. Now, this is something where we have to be very careful, right? Because we know that the range of cosine only goes from -1 to +1. And so here's where you need to know, what is the square root of 2? And if you don't know, grab your calculator and find out. But if you do that, you will find that the square root of 2 is approximately equal to 1.4. And that means that we will not find anything that satisfies either one of these equations because of the limitations of the range of the cosine function. And that means that for this particular equation, there is no solution.